In the next generation of machines, System 370, there was a new component in hardware called Dynamic Address Translation, or DAT, which would allow an address to be translated by the hardware into another address. The benefit now was that we could create an image of how storage looked and be able to resolve it to how it actually was. So I could reference something in system memory using a particular address, and the DAT feature could translate that into the address of where that data actually was in real memory. What could be done now was that when a programmer wanted 100K, we could provide pages from all over the system and present a virtual image as if these pages were all together in one continuous piece. Since DAT could translate the addresses being referred to into their real location, and vice versa, then we could avoid the fragmentation problem by ensuring that every unit of work that came in the system was run as if it were all in one virtual piece now. In addition, since all of memory was divided up into pages, the hardware could now mark a page when it was referenced. We saw in the first module how memory is staged into the higher level caches of the processor, so when this occurred, the hardware could simply indicate that a particular page had just been referenced. The operating system would then scan these pages every few seconds and turn off the reference indication and keep track of how much time had gone by since that page was last referenced. While some pages would be highly referenced, some might go unreferenced for long periods or even indefinitely. So if the system needed more memory to run work, we could take pages from anywhere and present the virtual image to the work. But also we could remove the oldest pages, those that hadn't been referenced, and move them out to disk, since they weren't being used and they didn't need to reside in memory. However, if they were referenced again, the system could bring them back in and processing could continue. The objective was to remove those pages that had the least likelihood of being referenced again. However, as storage usage became more intense, then we might find our system having to do more and more paging, bringing these pages back in from disk, which would incur a performance penalty because work would be delayed waiting for the page to come back in. The result of this transformation to virtual storage was to allow more efficient use of memory and allow more work to run in the system by minimizing such waste and ensuring that every available page was essentially capable of being used. Once this occurred, the use of partitions was abandoned and OSVS2 became the system implementation of choice. OSVS2 became MVS, which is the direct predecessor of ZOS. In fact, you will often see and hear that MVS and ZOS are used interchangeably. Since memory was being presented to work as a virtual image anyway, MVS introduced a new concept called the address space and also made some changes in the assigned storage areas. In particular, the CSA, or Common Storage Area, was added to provide a place for programs to place data they wanted to share with other address spaces.